Yes. Very good. Here. Okay. So let me continue with some additional consideration for design for the additive manufacturing. So let's say here, if you could see the overhanging geometry, so it means that those surfaces which are considered as the down-facing surfaces with respect to the building substrate. So generally speaking, it is defined by the overhang angle here. Mhm. Overhang angle here. So this can be overhead. Yeah, this can be the bridge, yeah, or defined with the overhang angle. Okay, I would not like to go into detail for the tables on the left side of this figure, but generally speaking, uh, there's no problem with the up-facing surface, with the vertical surface, but when we have the down-facing surface, when uh, the angle with respect to the horizontal line ranging from 90 up to 180, and you have to consider, and you can see the effect of overhang angle on the qualities of the down facing surface. So it is, if the angle is 40 degree, 45 is okay. 50, you see the surface become larger up to the 65. So we have a terrible surface quality, and up to the 70 degree, and the surface is not a surface anymore, and this is a failed print so you see the influence of the overhang angle on the quality of the down facing surface. And generally speaking, the down facing surface, the overhang angle should be restricted to the 45 degrees, but it actually depends on the technologies that you use: particle fusion, direct energy deposition, or the others. Depends also on material type, material form, wire powders, uh, powder size, distribution, yeah, and powder shape as well. So that's what you have to consider for the design for AM. Yes, and these overhang features require the support structures to support the down-facing surface. And if you do not want to add support structures, because support structure is a waste when you finish the 3D printing process, you need to remove. And then you should consider the overhang angle, which is smaller than the critical overhang angle. And in that case, the down-facing surface can be self-supported. This means that theta is 45 degree, and then this can be self-supported. It can be printed out without support structure for the down-facing surface. Cross-sectional dimension. So, for example, large cross-section may indicate larger heat accumulation during the process. Larger, yes, and these affect the thermal distortion. Yes, it's something related to the scanning strategy. Yes, because larger cross sections, which means that following the scanning vectors, the root of the scanning vectors in the position of the arrow, for example, and since the scanning speed is too high, and then you have the large thermal gradient if you have larger cross sections, and the thermal gradient leads to the formation of residual stress, and this the main reason cause uh, structure distortion, and so on. The input energy density. So we could discuss a little bit about the input energy density can affect the material. Yeah. If you have the insufficient energies, so you can not create the stable melting point, and it affect the accuracy and the surface finish. So if you have the insufficient energies provided to the uh, cross sections, to the powders actually, so instead of melting, for example, it's just provide a sintering, or even you have the, how can I say, unfused regions or unfused defect, which contribute to the higher uh, porosity inside the materials. Layer thickness, smaller layer thickness is okay, it's fine, because it's have to enhance the part accuracy. But then you reduce the layer thickness means that you enhance the number of the layer which need to scan. Or in other words, you enhance the time for manufacturing process or the cost associated with the manufacturing times. Yeah. Preheat, yeah. So let's say preheat can cause additional material distortion. We can reduce the accuracy. Loose powder attachment is one of the reasons. But on the other hand, yeah, we see that preheat can reduce the thermal distortion. Why? Because it's reduce the thermal gradient. Yeah, reduce the thermal gradient. So in some case, even have heat up the building plate, the substrate plate actually, because the plate and you have the part attached to the plate at the bottom surface of the part. And if you manufacture the the top layer of the part, and then the top layer is hot, but the bottom layer has pretty lower temperatures, yeah, and therefore you have the great thermal gradient between the top layer and the bottom layer of the part during the 3D printing process. And therefore, if you heat up the building plate, it also means that the heat will be transferred to the bottom layer of the part and reduce the thermal gradient between the bottom layer and the top layer, which under the sintering process at that time, and therefore reduce uh, the residual stress and reduce distortion. But then there are many factors actually influence the additive manufacturing process, and there are just some consideration, and people can separately consider the influence of these parameters. But if we combine, then the issue is more complex. Yeah, the investigation is more complex. And on the right side, you have some example of AM pots. Those are difficult to inspect. Mhm. Yes, and this they are some of the challenging work that people are focused are focusing on at the moment, because if you fabricate the complex part is okay, but then you need to examine whether the fabricated part have good accuracy or not in terms of the dimensional accuracies. So you have to measure the dimensions of the part. Mhm. And the inspection is also an issue for the moment. And, yes, because if the part has exposed surface, exposed everything exposed, uh, and the measuring tool can reach the surface, then it's okay. But if the fabricated surface is located inside the part, and that the measuring tools cannot reach these surfaces, and how can we measure the accuracy of the manufacturing process, or the accuracies of the part? Yeah, this is the point. And yeah. So mhm. Let us discuss continue with the continuously continue to discuss with the support structure design. And generally speaking, this is the undesigned portion because is the waste materials, and after uh, the additive fabrication, you need time, you need effort to remove the support structure. But for many cases, you need the support structure to support the down-facing surface, like the surface C and D, or the part here with the large overhanging angle, especially those surface C or D. For the wet fusion process, yeah, generally speaking, you use the laser or electron beam as the high energy source in order to melt the porous materials, and with the high scanning speed. Yes, so you have the thermal gradient in different region of the part, especially the large part with large cross section during the 3D printing process, and this is one of the reasons for that we need to create a support, because the support structure is not only used for supporting the down facing surface, but can also use as a mean to dissipate heat, to transfer the heat to the building plate, and therefore we can uh, reduce the negative effect of thermal gradient caused by thermal gradient. The additive manufacturing pre-processing software can automatically generate the support structure, as I already mentioned to you, especially for those surfaces having overhanging angles larger than 45 degrees. But as I already mentioned to you, despite using this software, if you run the simulation, and you could see that okay, the use of software is not enough for the automatic generation of support, and we need some some manual work, so by human, to add additional support structure to guarantee the stability of the structure, especially during the 3D printing process. And we have various types of support structure, which can be represented on the next slide, not this slide, but you have the point support, web support, like the spider web, uh, line support, block support, contour support, and so on. And depending on the type of support, you will have the different contact between support and part. And the contact area can be points, lines, area. The larger area of contact, so the harder to remove the support from the part after the fabrication, for sure, because this is the wetting process. Yeah. The larger the area of the joining area, and the more difficult to remove the support from the part. But generally speaking, yeah, we have concave fillet here. We have convex fillets here. They can be considered as down-facing surfaces with respect to the horizontal line. But then these surfaces are considered as the cell support, yeah, structures. So there's no need to add support here. This is a special thing. Yeah, it's special. So as I already mentioned to you, we have a different type of support structure. We have the block support, point, web, lie in the spider web, contour lines. And practically you can combine. So for one surface, for one down facing surface, you can use both the block support and point support together. Yes, in order to enhance the stability of the structures. Yeah. It depends also on the weight of the part itself. Generally speaking, the block support for bulk geometry, line support for supporting small features, contour support for sustaining the contour of the part, the bow of the part. Support structure design depends on personal experience. So yes, I agree that the software can help you to generate the support structure. Then it needs to modify. Generally speaking, to add more support to a certain region and eliminate some unnecessary support generated by the software. So modification is needed. And that's why we would have to say that the support structure design depends on the personal experience. Over design means that you waste materials and you may face with challenge regarding removing the support, yeah, after the 3D printing process. Of course, you can reduce the amount of support structures by selecting a suitable orientation of the part to reduce the amount of down-facing surfaces. But then, in doing this, you may tend, tend to increase the building time. You may tend to increase the building time. And regarding the support structure remover, this means that you cut the support from the surface of the part. And you may damage the surface actually. And as the result, those surfaces which are critical and cannot be scratched uh, and others should avoid to use support structures. So what you need to do is to select the appropriate orientation of the part so that the critical surface will not have support structure. So that is not always possible to do. Yeah. That's why we said it depends on personal experience. Yeah. In addition to the help of the software. The block support the hard spacing. Hard spacing is actually the smallest distance between the two scanning vector. Or in this case, the space between the neighbor support line. I'm sorry because I mixed with the hard spacing when scanning the energy beam, the energy beam, like the laser. But in the case of support, is the space between the two neighbor support lines, two adjacent support lines, and the small hash spacing. Oh, I'm sorry. Vâng, xin lỗi. Uh, where am I? Okay, yeah. Yes, support, where am I? Affecting the density of the support. So let's think of the fact that if you reduce the space between the two adjacent support lines, and then you can increase the density of support, which means that you use more material for creating the support. Yeah, stronger support, so and smaller thermal residual distortion. Why? Because you enhance the degree, the means in order to promote the heat dissipation from the part to the building substrate, and therefore you reduce the risk, or you reduce the level of thermal gradient in the part. Mhm. Like in this case, you can see on the right side. You can see on the right side. If you align the part uh, vertically, so you use least support. This means that when you build up the part, yes, is in fact you waste less materials, but then the heat transferring from the part to the building substrate will be smaller, and and therefore you have the risk of distortion. Yes, because we have a last thermal gradient between the bottom area and the top uh, area of the part. Yes. So comparing to the case of lay the part down on the on the building substrate, and then you have a lot of support structure, a lot of support materials, but then you can uh, transfer the heat faster to the building substrate, and at the same time you reduce the number of layers of scanning because the head of the part is reduced. Yes, and therefore you can shorten the fabrication time, but then orient the part 45-degree respect to the horizontal line, and then you have the structure so-called easy to remove support. Yeah. Yeah, because if the support is attached to the exposed surface, and then it's quite easy for you to remove the support and to polish the surface. But if the support located inside the part, and then how you can yeah how you can remove the support from the part, yeah, is more difficult. Support bar teeth reduce the contact between the support and the part, so you have easier remover. Yeah. and so on. But you can read, yeah, you can read more here. I don't want to go into detail regarding the support structure because there are many things associated with support generation, and if you play with this, yeah, in the real process, you will see that how complex it is. It can be easier, but it can also quite complicate, depending on the purpose of the designer. Uh, and we can when we can apply the cellular structure to support the part. Yes, this enhance the material efficiency. Uh, yes, because these are cellular structures. This means that you reduce the material waste. At the same time, it's easier for us to remove the support structure from the part. Yes, afterwards. But for the moment, we do not have the complete theory for guiding the selection of the support because everything is under development. Yes, it's not easy to investigate the support structure like the gyroid cell or the diamond cell or the sparse cell and so on. It's the untraditional support structures. So we are more familiar with the truth support structure, truth support structure. The cell support can encounter such an issue at support part interface because of limited contact points at certain areas. Transition layers can be fabricated. Yes, if you could see on the right side, you may have a transition layer to reduce the thermal residual stress and better surface finish. Because when we remove the support structures, yes, it's easy to detect the transition layer from the standard layer of the part. Yes, so which help to enhance the quality of the surface after eliminating the support structure from the part. And for the for saving money purpose, building time and material efficiency for each cellular support need to be carefully considered. Yeah, for sure. What is it? Okay. Design for lightweight structure is actually some kind of imitation with the natural structures. Like in the case of cellular bonds, the bond of the human body is actually the cellular cancellous or porous structures. Yeah, but it withstand quite well the impact force. Uh, yes, quite well on the impact force. So this is help to minimize the mass while maximizing the utilization efficiency of the materials. Because the reason with low stress do not solid materials, so we can eliminate the material in the regions having low stress, and therefore you can save materials and design the material to those areas having high stress or high stresses. Lightweight means high strength to weight ratio, high energy absorption per weight ratio, low thermal conductivities, large surface area to volume ratio, mean that you are benefited from uh, with the product reliability, energy efficiency, and product sustainability. It means that you use less materials, create less weight, yeah, and save the environment, and therefore you have the product sustainability. However, lightweight also mean that you have geometric complexity. You could see how complex the internal structure of the bond is, and this is challenging for the trades in the manufacturing process. It is an opportunity for AM in order to fabricate the part. Yeah. Khó khăn với người nọ là cơ hội của người khác. And there are several natural structures that you could find in nature, yes, like honeycomb structures, sponge, bone, so on, which you can imitate to fabricate the several products. Yes. And now I would like to consider the topology optimization for lightweight structure design. This is also the design for additive manufacturing. So in some case, the design doesn't only mean that you start from the sketch, you design a 3D object, uh, it's been designed. And sometimes, yes, you already some kind of original design. You run the optimization or structure the optimization to, let's say, optimize the performance or the width of the part. And these can also be considered as the design step for AM. And practically, yes, this is widely used uh, uh, for designing for AM. But what is the topology optimization? Sorry. Topology optimization is actually the math tools to optimize material distribution within a given volume. So we can say this is the design space or design volume, and the other will be preserved with objective is goals of minimize or maximize constraint like minimize weights, maximize stiffness, minimize compliance, and so on. Minimize compliance mean maximize stiffness actually. Topology optimization is based on the finite element method, relying on the discretization of design space mean that to match the volume. Mm. During the optimization, elements are selectively removed by algorithm, and process is iterative until achieving the satisfactory result. Yeah. So one of the famous algorithms that can be used for designing AF structure called solid isotropic material with penalization. So it's called SIM. But in addition to SIM, there are other methods. But I would say that embedded in many commercial softwares, SIM are widely used. Is widely used. Is widely used. The other, yeah, have been investigated, but they are invested by coding in MATLAB, but not already embedded in in the commercial software. And in a little bit more detail, SIM turn the topology optimization into the consideration of density optimization, and the material density is penalized. Penalized means to remove, yes, or to eliminate elements with intermediate density. This means that when running SIM, the material will be, the elements will be assigned with the value in between 0 and 1. 0 is mean free volume and 1 is mean solid materials. Uh, but the intermediate density material has have actually no real physical meaning because in practice we have 0 or 1. 0 mean free volume, 1 is mean solid materials. There's no material with 50% relative density. This is the imagine volume or virtual uh, density. But then, as I at least one time I have mentioned to you, we have to define the critical values of relative density. For example, zero point 0.6, and those elements with intermediate density, if uh, they possess the values being larger than zero point 0.6, and this element will be assigned as 1. So turn everything to 1. to solid material, and the others will be eliminated and considered as the free volume inside the design space. So that's the idea of SIM, solid isotropic material with panelization. Bezo and PTO and the other methods, the other algorithms that can be used for the topology optimization. You can read more if you want. And there are several software actually that can be used to run the topology optimization at the moment. So for example, Unter OptiStruct, yeah, to give you offer a powerful tool in order to run the topology optimization at the part. Unter Solid Thinking Inspired, yeah, is also a famous software, and the user interface is more friendly comparing to the Unter OptiStruct. And this, yes, Autodesk Shape Generators is actually an add-on of the Autodesk Inventor, as I remember, just an add-on. It's not really a software package, but it's just an add-on. There are several optimization, structure optimization, for example, site optimization, shape optimization, topology optimization. Yes, and yes, and here is some kind of a little bit more detailed description about the topology optimization uh, for lightweight structure design. Uh, this is, for example, this is just an example of the topology optimization of an aircraft wing. So the external cover in red color, this is actually preserved volume, and everything in between or inside the red region represented in blue colors consider as design space or design volume. And the design volume will be modified during the topology optimization run. Yes. And during this run, those material which are unnecessary to present will be eliminated from the structures, and we have the topology optimization of the wing. But of course, we have just the sub part of the wing. So we do not consider the whole wing. I mean the writers or the authors. So as I already mentioned, we need to define the design space. Yeah, in blue color. It actually depends on us whether we select the blue or the red. Yes, it's possible to select. This is up to us. The constraint volumes or the preserved volume, the boundary condition in terms of the loss, constraint, temperatures, and so on. The objective can be maximize stiffness, yeah, or minimize weight, whatever you want. If you think that maximizing stiffness is more important, and then you select for optimizing the structures. The case is mean that the regime that you consider for the optimization. So mainly refer to the static mechanical problem. If you have some kind of vibration, you have the others, and it's not possible to solve at the moment. The structure optimization just provide you the concept design, and after finishing the process of concept design, you may need to modify to be suitable with the additive manufacturing, to add some necessary feature probably like powder release channels, stop allowance, and others, and then check again with the simulation software before you are sure that uh, it's possible to print out the design. So if you want to investigate in the mountain physics problem, uh, thermal, mechanical loads. The other type of loads, dynamic loading problems, and fatigue. Ooh, it's quite difficult. Yeah. And code software, for example, can be used to analyze the fatigue properties of the structures, but then the ability is still limited. And the issue is topologies may create a structure with very small size. And please remember about the minimum wall thickness. Yes. If it's too small, then they are not feasible to be printed out by the Butterfly Fusion AM process, and maybe the other. Because Butterfly Fusion AM process can fabricate with the layer thickness down to 20 microns. So this is a small list layer thickness, and other should have the thicker layer thickness. So, but it is the smallest layers. Even with the smallest layer thickness of 20 microns, the minimum one thickness uh, for printing out by this technology is around 1 millimeter to guarantee that there's no defect occurs during the manufacturing process. So, so that's why we need the human here. Yes. To eliminate some features that are not feasible to print out by the manufacturing process, like additive manufacturing. Or feature with fast changing cross section, because you know that with fast changing cross section during 3D printing, we have a risk of distortion. And because of thermal stress concentration, and and the issue is that during the FE analysis, we do not consider the anisotropic properties of the material. This is extremely difficult. And in fact, many considerations, people still consider the material have has, for example, isotropic properties. This is an issue. There are many issues actually. Yeah. So if you have enough time, you can consider the topology optimization in terms of the math representation, in terms of the power law, and the reference is available for you to read. And let's say several months ago, is might be the case that you cannot download the paper, but now you have an account from the Vietnamese National University, and then can download the the paper. Not all, but many paper can be downloaded. So, and here are the examples regarding the topology optimizations employed to create the lightweight structure design. So for example, in the first case, you could see that is some kind of frame where the green gray color areas represent the preserved volume, and we have the fixtures associated with the gray area, and the brown color assigned as the design volume, which can be modified during the topology optimization run, and the others of course must be preserved. And after the run, you will have the, the obtained structures. So the software automatically eliminates the elements based on the constraint that you have set up, based on the objective that you have set up, whether this is the minimized width or the maximized stiffness and so on. But please take a look at the result of the structures. So this actually has the set of those elements And therefore, yes, it is just the result of the process of topology optimization. And then you need to translate the result into the model that is smoother and feasible to be printed out by additive manufacturing. So not like this, because it's not uh, so attractive. Yeah. So how you can attract your customer to buy this type of structures? No. Then you have to modify. Yes. To create new structures. So it's quite easier to see on the an example provided by EOS. Yes. This is the 3D printed satellite components, and initially you have something like the arm, like it's called the antenna bracket initially, and after running the topology optimization, and you have the redesigned antenna bracket. Yes. For this type of frame structure like this, so you can somehow measure the part in terms of the dimensions. Yes. And on the right side is an example of created by Formlab for topology optimizations. So initially you have the original structures that contain solid materials, and it has the possible to be modified by topology optimization to eliminate unnecessary materials at the low stress areas. And after running the topology optimization, you have the result with many elements, the small elements, and then you convert the design with many elements into the smoother structures. It's called topology optimized structures. And then you use the simulation software in order to virtually examine the behavior of the part under the influence of the given forces. Yes, and last but not least, you export if it is okay, and then you export the model in the form of the SDO file, and then prepare for the setup with, for example, AutoDNet file, and materialize to make it ready for the 3D printing process and the others. The others. And last but not least, this is just some kind of guidelines that I have taken from a MPDI journal to to provide some kind of instruction for the structure for the selective laser melting process or hybrid selective laser melting, together with characteristic that you should consider. So, for example, if you print out the cylinder like this, so generally speaking, the diameter of the spin or the cylinder need to be larger than 1 millimeters, let's say. And if you want to print the bar like this, and the thickness of the bar should be at least 0.2 millimeters, and so on. But actually depends on the material, depend on the input material, depend on material itself, depend on the form of the materials, depend on the parameters that you use to synthesize the materials, the technology itself, for example, the back fusion or direct energy deposition, and others. So uh, they are the things that I would like to highlight here. So please refer to that. And of course, there are many instructions online, and you could check. But for preparing the lectures, I would like to refer to some published paper that already been reviewed by reliable researchers. So the content should be reliable rather than selecting some information on the internet, and yeah, it's not really good in that case. And when you find something to refer to, especially the paper that you uh, would like to refer to, summarize the content in your report or assignment, and then you should refer to the reliable journal papers. Yes, and please keep in mind that you have to sign the paper that you refer to. Otherwise, you took information from the paper, and it may be considered as the plagiarism. That one. Yeah. Uh, Multiple consideration in terms of the design for additive manufacturing. So, manufacturable. For example, if you have a hole like this, and if the diameter of the hole is smaller than 0.5 millimeters, and then you do not need to add the support structures. You do not need to add the support structures. And if you want to create a support structure and the size is a little bit larger, and then the top surface you can modify so it looks like a droplet. Yes, so it's manufacturable for the down-facing surface, and you do not need to add the support structure here. But then the pie with the cross section like a droplet look not really attractive, I would say. And this is the reason where the scratch is concentrated. Yes, because you have the sharp edge here. And here, for example, you have the pie with the internal free volume inside, like a pipe. So the thickness, yeah, uh, the inner diameter inner must be larger than 0.4 millimeters. Otherwise, during printing process, the two surface for some errors, you can yes close the internal channel. Yes, this is the mistake. This is the tolerance of the accuracy of the 3D printing process because the low resolution and therefore the holes can be closed. Yes, that's the reason you should maintain at least uh, 0.4 millimeters in terms of the inner diameter. Now let me continue with the chapter 6. So just some slide. Yes, it's not enough energy. Yeah. And hopefully that you can follow the content of the lectures, absorb some kind of knowledge, and try to read it and read them at home and to remember as many as possible. And hopefully, at the end of the semester, when are at when you are in front of me to answer the question regarding the assignment, you can do it well. Hopefully. Okay. So let me fire. So the chapter 6 contains more or less than 20 slides. Chapter 7 around 15. Chapter 8 is just some instruction, and chapter 8, from a point of view, give you some idea about the new entrepreneur form. Yes, because now is the fourth industrial revolution. You have the fourth industrial revolution. So the new form of the company appear actually, and yeah, this is business opportunities, and we do not study actually the business administration and so on. And for these things, could treat them at home for the chapter 8. For the chapter 6, we consider the design parameters for the additive manufacturing. So it's called process development, and chapter 7 is regarding chapter 7 post processing. Yeah. So the two things. The most important thing from a point of view is the materials, uh, design for additive manufacturing, and some important consideration in the first chapter. Yeah. As an educator, I see everything is important. Yeah, everything is important. Mhm. But if you have any question, just do not hesitate to ask me. I'm here to help you. So now, just some slide before we can start for relaxing. Okay. Parameter selections. So process parameters you can for these parameters it will be considered when you're setting the machines. The aim is to achieve the desired deposit, the part requirement, and overall quality. Yes, for sure. Uh, and for the supplier, it means those company who develop the machines and to sell the machine to the market. They they develop the standard set of parameters for their machines, and they also develop the materials, for example, powders. So if you do not want to do some kind of research, so in that case, you should refer to the parameters developed by the printer suppliers. So you save cost and time for the investigation. They did it for you. They did it for you. And with the proposed set of parameters suggested by the AM machine suppliers, you would have the highest possible properties uh, of the material after the 3D printing process. Uh, but since this is matter of money, time, and effort, and generally speaking, the standard parameters will be protected by the encryption, and basically you cannot see or modify them, and you need to purchase for the license to see each set of parameters for a certain type of materials. And even if you can see, you need to keep them confidentially. Yeah, because it's protected by the copyright. Yeah, for sure. Money, time, effort. Yeah. Therefore, it must be protected. AM process is complex, so you need time and effort to develop the process parameters. Yes, at least you are researchers doing some kind of research associated with consideration of influence of a certain parameters on the final properties of the parts. Otherwise, you should not modify. Mhm. Because the modification can result in the negative result, and you lost time, you throw money away. Yeah, it's unwanted. Trial and error approach might be used to optimize the deposit material, sure, but then it's a matter of money. And production parameters and challenge. You have more than 180 parameters for additive manufacturing process. So these can be divided into different steps or phases. And during the design phase, you can consider the geometry, you can consider the overhang because the overhang angle will be used in order to identify which surfaces need to be supported by the supporting structures. And the definition of the support structure itself, whether this is uh, the, the net support, whether this is line support, whether this is the block support, and so on. What about the density of support structures and how it's attacked to the surface of the part, and how we can consider uh, the connection so that after the 3D printing process, the support structure can be easily eliminated from the the path surfaces. Material is also an important topic because the material type, yeah, aluminum materials, stainless steel material, nickel-based superalloys material, and so on, will have a certain influence on the final quality of the part, at least in terms of the strength, uh, the ability to withstand heat, ability to resist corrosive environment. Yes. And you may have to consider the powder size, powder purities, because the powder purities will influence the corrosion resistance, yes, and even the strength of the materials. The layout, it means that, generally speaking, if the building channel is large enough, and if we just print out the small parts, and for one view, you can print multiple parts at the same time. So you can consider the horizontal or vertical orientation of each part, and the one part with respect to the other part within the same print, and how we fill this print part within the volume of the building chamber to improve the efficiency of the printing process. And the process itself, yeah. So there are many factors, many parameters associated with additive manufacturing, like the heat source parameters, like the laser intensity, the scanning speed, the spot size, so on. The exposure pattern, and we have more than 180 parameters combining together, and this is really, really complex. The post process, yeah, how to eliminate the support structures, how we can modify the properties of the material toward the properties enhancements. So based on this, we can select the suitable heat treatment processes or other type of processes like shot peening to enhance the fatigue properties or polishing to enhance the quality of the surface of the materials. And these will influence the object accuracy, surface qualities, and material properties of the parts. So I think I will now present the last slide for today. And on the last day next week, I will try to complete the chapter 6 and chapter 7. And for the chapter 8, it's just some introduction about the business opportunities. Yes, we have a lot of business opportunities actually, especially for the additive manufacturing, because we have talked in the chapter 1 about the sustainability advantages of using AM. So in near futures, that you will see the benefit of using AM, yeah, practically. But for the moment, we could anticipate, we could predict the benefits of using AM in fabricating those parts for industry. Yeah. But let's say chapter is something which can be used to remind the content of chapter 1 in terms of the sustainability advantages and challenges of using AM, and some aspect regarding the business opportunity. And again, this can be read at home. And for this slide, uh, we consider the parameter selections for parameter fusion process, and in this process, we can classify the process parameter into four categories. Laser related parameters, and you may be interested in laser power. Yes. Please remember, if you use the very high laser power and then the energy is provided is too large, and those uh, alloying elements with low melting temperatures can be evaporated, and then you lost the elements, and the content of the material or the composition of material is modified, and then you will have yeah, the modification in terms of the properties. In other words, properties in different positions will be different, and it's quite detrimental. At least in on the same layer, you would have some problem like this, and you would not like to have the low laser power because you would have some kind of unfused defects which contribute to enhance the porosity of the material inside the materials. The spot size, the punch duration, the punch frequency. So this is something that you learn with the laser punch. Yeah. So this is a matter of optic. Yeah. Scan related parameters. So we may consider the scan speed. If the scan speed is too fast and the laser power is too low, so the heat transfer to the powder is not enough, and then you could see the problem. Scan spacing. Yeah, there will be another slide show you the effect of enhancing the spacing between two adjacent scanning vector. Yeah, scanning pattern also affect the properties of the material. Powder-related parameters like particle shape, spherical or irregular shape, size, and size distribution, powder bed density, layer thickness, and material properties. And please keep in mind that enhance the layer thickness, we enhance the effect of staircase, and therefore making the surface quality poorer or rougher. Temperature related parameters, we are talking about the powder bed temperatures. Yeah, but the feeder temperatures and temperatures uniformity. Yes, if temperature is uniform, is good. Yes, because we can reduce the thermal gradient and therefore reduce the stress accumulation or reduce the degree of uh, residual stress. The problem is that these process parameters interdependent and mutually interacting, so one will affect the others. Is an issue. One will affect the other, and the combinations of effect of these parameters, yeah, and how they influence how they affect the qualities of the finer of the printed part is quite important to investigate. And some basic process parameters that you might be interested in, for example, but please keep in mind that you have more than 180. But just list here some basic parameters. For example, the laser power is the energy emitted by the laser per unit time, typically using the source having the power smaller than 400 watts. The spot size of the laser, for example, this is the diameter of the focused laser beam. Where you can see from here is the laser is focused onto the materials. The scanning speed is the rate of moving spot across the powder bed along the scanning vector. The half distance is actually the distance between the two adjacent scanning vector or the neighbor scanning vector. The layer thickness, yes, we know. Okay, so I think it's enough for today. Yeah. Leave at this is the slide 5. So I will note here, and the next time I will start with the 6th slide, and hopefully we can finish. Okay, don't worry. And thank you for your attention, and hope that you have a wonderful day ahead. Goodbye. And please remember that I'm still here if you have any questions. and I just here to check your attendance. And mhm. Thank you and goodbye.